bardzo dziękuję. A tutaj wiem już, jak zrobić te prezentacje.
Jeszcze nie mamy. Co mogę zrobić teraz? Tak. Po prostu.
Nie tak, że nie masz racji, po prostu słów. Nie, spijesz ten pomysł, w sensie, że nie masz racji. Może to dokładnie.
Good afternoon, everyone. It's a pleasure to see you all here at the last seminar of this semester, last official seminar of this semester, because next week we'll have one extra one. And today we're going to have a talk of Maciej Lisicki. I will introduce our guest in a moment, because before you, if I may, I would like to welcome also among us the interns. So the laureates of and finalists of the Astronomical Olympics, from Astronomical Olympics. So you can maybe stand right now. There's 6 of you. So we have some very smart people, also like young people, and we are happy to host you here. So you will be here over this week. So if you have any questions, here's the crowd of students, researchers, and PhD students also of this institute. So feel free to answer to ask any questions. And the speaker of today, Professor Maciej Lisicki from the physics department, is a physicist, so it's not an astronomer, but working on some fluid mechanics, and it's an expert actually in this field, but he's known among the researchers of the physics department, and not only, as the one who actually hosts a lab that has also a coffee lab there. And they are actually doing research related to fluids, especially coffee. And Maciej graduated physics at the physics department here at University of Warsaw. He spent some time in Germany. He did his PhD here in Warsaw, and then he moved to Cambridge, UK, where he spent several years, and now he's back at his alma mater, so University of Warsaw, and we are looking forward to listen to your talk.
Thank you very much. Thank you. Right. Okay, so thank you very much. I'm very grateful for the invitation, and today probably for something completely different to what you're used to hearing in this room. I'm going to talk about the physics of brewing the perfect coffee. Now, what is the perfect coffee is entirely a cultural thing, so I'm not getting into this debate, but I can tell you what the physics of the brewing process is. But before we lurk into that, well, you had the chance to try some of our coffee just before the seminar. I brought 2 bottles, and I see they're all empty now, so you had the chance to try filter coffee. Today I'm going to talk predominantly about espresso, which is a bit of a different game. So before we dwell into that, maybe a word about what is coffee. Well, from the scientific point of view, it is an evergreen shrub. The Latin name is Coffea arabica or Coffea canephora, so arabica or robusta coffee. Now, robusta is by far the most popular species. Arabica is the one that we're most used to. So it grows, well, it's a green shrub that grows up to 3 to 5 meters tall. It's got these beautiful dark green leaves, but of course we love it for the fruits. And the fruits are red or purple things called cherries, and these cherries contain seeds. Now these seeds thank you. Actually, I like the old-fashioned way, but these seeds that are here are the coffee beans. Now there's various ways of processing these coffee beans before we roast them, and after we roast them, we make coffee out of them. So coffee grows in this belt between the Tropic of Cancer and the Tropic of Capricorn. So this is the area where you can find coffee shrubs, typically quite high above, so 600 to 2,000 meters above sea level. And it is thought that it spread from Ethiopia and through Yemen and now it's all over the place. Now, for developing countries, it's the second most valuable commodity. So many economies, especially of poorer countries, depend on coffee, and it's widely consumed. It's estimated that almost 2.5 billion cups of coffee are consumed every day, and we contribute to that every moment. Because it grows in these areas, it is prone to climate risks, and therefore the prices of coffee have been rising quite substantially. Well, I guess each and every one of us has a personal relationship with coffee. But what is coffee for a physicist? Well, it is a porous medium. So the problem of brewing espresso is essentially the problem of flow of hot water through ground coffee. So ground coffee is a porous medium which has coffee grains which might be smaller or might be larger. And so water infiltrates these void spaces in between, and on the way it dissolves the material, and that's something we see in this beautiful flow that emerges at the bottom part. Of course, there's different methods of coffee preparation, like French press. I'll come back to it. But because this is a flow of fluid through a porous medium, and this flow is governed or induced by a pressure difference between the top and the bottom part, now the sort of standard go-to treatment would be to relate this flow rate to the pressure difference or the pressure gradient that induces this flow. And well, what comes at the rescue is Darcy's law, which is a phenomenological law that describes the flow of fluid through a porous medium. And the Darcy's law states that the flow rate, so the amount of water that flows per unit time, is proportional to the pressure gradient that causes this flow. And the coefficient of proportionality here is proportional to a quantity called permeability. So this is a material characteristic, and inversely proportional to the fluid viscosity, which makes sense intuitively. Now, this pressure gradient might come simply from the presence of a gravitational field, which happens in filter coffee, where you just pour water over coffee and it seeps through, or it might be externally imposed either in an espresso machine, or there's some intermediate stuff. One piece of equipment I've got here is called an aeropress, which is essentially a big syringe where you load your coffee. It has a sieve, and you push hot water through this coffee. So then you get moderate pressure gradient. So the typical pressure gradient in an espresso machine is 6 to 9 bars, but this is what we're going to talk about. But coffee is more complicated than an ordinary porous medium. So this Darcy's law is very good for describing the flow of water through, let's say, sand. So something that is granular, but coffee is more complicated because it also, for one thing, it dissolves, and for another thing, it also swells upon wetting. So when you wet coffee, it increases in volume. So what happens there chemically, that's a whole different story. But there is swelling, there is chemical effects of extraction, and that all affects sensory properties of coffee. And well, now the sensory properties, there's some complicated chemistry that goes into it, and I will not comment on it today. But let's restrict our attention to espresso. So espresso, there is a notion of a perfect espresso. How many of you are espresso drinkers? Some. So there is a notion of a perfect espresso, and the perfect espresso that is a coffee that is, well, sweet, but not too bitter, but not too sour. So there is a balance between sour and bitter, and this depends on many things, but in particular, it depends on how long you brew it. So typically, if you brew your espresso for 20 to 30 seconds, you get something that could be called the perfect espresso, that is just right sweet, just sweet enough. Now, if you brew it for too long, you start extracting different chemicals, and that gives it a bitter or an ashy taste, and that's called an over-extracted espresso. Or if you brew it for not long enough, then, so typically less than 20 seconds, then you have something that's under-extracted, so it has these vegetal or sour notes. So we don't want either, so we want to brew it for just the right time. Now, how do we make it so that it brews over 20 or 30 seconds? Well, to brew coffee, you need essentially 3 elements. So you need coffee, you need your material, you need a grinder, and you need an espresso machine. And so this is a set that's necessary to brew decent espresso. Now, to quantify a cup of coffee, there is a specialist organization called Specialty Coffee Association that has outlined some standards as to what is a proper coffee. For example, well, they are formulated in terms of dose, also how much of the dry ground coffee powder goes into the machine. For a double espresso, this is typically 17 to 20 grams. Now, how much coffee you get out of it, typically there's a 2-to-1 ratio, so twice the amount, so 34 to 40 grams. But this extraction should take you 25 to 35 seconds. So to get exactly this amount of fluid. Now, another factor is the extraction yield, so how much of the dry coffee has been dissolved in this coffee pot. And another parameter is TDS, total dissolved solid. So how much of coffee is, how much of your coffee is actually coffee? So the amount of coffee in coffee, and that's typically 8 to 13%. So these are the metrics that the coffee industry uses to characterize a cup of coffee. Now, if you look at the diagram of TDS, which quantifies the strength of coffee with the average extraction, so how much of the soluble substances you actually dissolve, there is a sweet spot in the middle between under and over extracted, between too strong and too weak. So people are generally aiming to be in that area. Now, if we start to decompose the process into its basic elements, we start with dry ground coffee. So coffee after roasting, it is grounded, and ground coffee. So this is probably the first illustration ever of ground coffee, 1883. Now this is our microscopy image. It's not perfect, but you see the scale bar here is about 100 microns. So the typical particles, so first of all, are not spherical at all. So this is not like sand. But second of all, it's a very heterogeneous mixture, as in there are particles of different sizes in the mix. Okay, so one thing you can do in order to characterize this variety of sizes and shapes is you can do laser diffraction on this ground powder. And this is what we did in the Center for Biological and Chemical Sciences at our university. And so these are typical laser diffractometry results. So these are the distribution of particle diameters, so particle sizes versus well, the amount of particles. So it's a histogram of the distribution of sizes of ground coffee beans. And so what we see here is that these ground coffee beans, they range in size from 10 micron to 1,000 microns, so to a millimeter. So if you look at ground coffee, you will find just grains of different sizes. But what's important for this distribution, there is one large peak here for large particles, about 500 microns in size, and these are called boulders. So these are the large bits. And there's a smaller peak here, and these are called fines. So it's a mixture in the first sort of simplest approximation. It's a mixture of large and small particles, so a binary mix. Now, if you have a grinder, a coffee grinder has this setting which you can grind it to a half or 1 or 2 or 3 or 5. That number means nothing. So these different colors are different settings of the grinder, and indeed. So what it doesn't change the shape of the distribution, it slightly shifts the peaks. However, for the taste of coffee, it makes all the difference. So it's a fairly complicated phenomenon. Now, depending on your favorite method of brewing, if your favorite method is an espresso, then you typically grind it very finely. So something called espresso salt. So this is where the coffee grounds are the smallest. So these are probably the darkest bands here. Now, and the next step is AeroPress. So this giant syringe. Well, then filter coffee, Chemex, which is another type of filter coffee, and then the coarsest. So the yellow perhaps here is good old French press. And so depending on your favorite technique, you ground it differently. Now, in our case, we wanted to characterize the physics of brewing espresso, so we wanted to establish a protocol first that we would follow every time to brew always the same coffee. And I think among the Warsaw coffee shops, our espresso is the most repetitive. So what's the procedure here? Well, every time we use the same coffee, so this Brazil Igarapé rainforest, so this is the coffee varietal, natural, this is the method of preparation of the grains, from the region of Minas Gerais, from the Warsaw Roastery Coffee Lab, who are instrumental in our research, as they donated to us this coffee, because we wanted to have it every time the same, so we would have it 2 weeks after roasting. So every time we were to do measurements, we would ask them in advance to provide us with coffee 2 weeks after roasting. Because what happens is in roasted coffee, it releases CO2. That's why if you wait half a year for your coffee to release too much CO2, if you brew it, it's not tasty. So there is a window where coffee is actually good. So this CO2 is what makes the crema in an espresso, and the CO2 is actually important. Now we have a grinder. The grind setting was 1.9. It doesn't matter. But then the preparation method is, well, first we weight the dose. In our case, it's 18.5 grams every time. Then we grind it. Then we shake the ground coffee so that we make sure that it's as homogeneous as possible. Then we stir it with needles. So this is a 3D printed acupuncture needles that are used just to homogenize the coffee. Well, you can skip that part, but you want your coffee to be as homogeneous as possible, and for the reason that I will explain later on. So we shake it, we stir it, and then finally we tamp it. So we push on it with some force, and this tamping step is also important in the preparation. So in our case, normally this is tamping happens with a device that's handheld and just the person does it. We had an automatic tamper that every time would exert a force comparable to 20 kilograms placed on our coffee. And of course, this world of coffee is very much for nerds. So there is all sorts of equipment you can buy, and this equipment comes in various. You can buy everything made of gold and pay however much you want to pay for that. But a typical coffee machine, in fact, is not a very complicated design. Of course, this looks complicated as a technical solution, but what it boils down to is the following. So this is the coffee machine we have in our lab. Well, it's connected to a water supply. The water goes through a rotary pump. This pump is connected to a pressure regulator. Now we have a pressure sensor connected to it. Then water goes through this flow meter. Then it goes through a boiler. A boiler is basically a big tank of water that is pressurized. It's held at about 120 degrees Celsius. So the water that makes your coffee goes through this boiler, and it gets in thermal contact with this water and heats up to about 96 degrees Celsius, and then it ends up in this device called portafilter, and then it ends up in the cup. And underneath the cup we have scales, and so all the data from these three we measure. So we gather simultaneously using this computer and the tiny Arduino that's the scale. So this is a very simple experimental setup that we have. And so let's brew. Well, this is actual photo from our lab. And the typical experiment looks something like that. So maybe you can't see that very well. So panel A is mass in the cup versus time. So what happens is initially there is very little flow. So first of all, we have droplets of coffee. So the mass increases slowly. Then there is a crossover, and it starts increasing more rapidly. Now, if you translate the mass to flow rate, which is essentially a time derivative of the mass in the cup, you'll see that, well, initially the flow rate is small, then it increases, but then interestingly it saturates. And this happens, so this increase happens over about 30 seconds, and then later on it is saturated. And now the pressure signal in the machine, in this case, was 6 bars, and this was consistent throughout an experiment. So what we see here, in fact, are two regions. So first is the short time regime when water infiltrates the puck. So initially the puck is coffee mixed with air. So this water has to displace the air from the porous medium and starts dissolving the coffee. So there is infiltration, there is swelling, there is displacement of air. Then finally, when there's water in contact with the coffee, there is dissolution, and finally espresso starts flowing. So this is quite a complicated regime with lots of things happen. It's a multi-phase flow, multi-scale. It's a horror to model, really. Now, interestingly, there is also the long time part, which is the times where we would normally not be brewing our espresso. So I told you that the perfect time to brew an espresso is about 35 seconds. So the long time regime happens just after. So if we leave our coffee, maybe you like a longer coffee, you can leave the machine on for longer. Well, then you enter a different regime where the flow stabilizes. So the flow rate starts being constant, which means that the dissolution is complete. So you have dissolved everything that you could, and what's pouring out of the machine is essentially dirty water. Okay, so we have these two regimes, and we were interested in understanding what's going on in both of these regimes, and particularly because in our coffee machine we can change the pressure. We wanted to understand how this flow rate behaves at different pressures, because we would normally expect from Darcy's law that at higher pressure the flow rate will be higher. So let's see. One more thing that we did is we wanted to characterize the dissolution. So we wanted to understand how this material is being dissolved. And so what we did, we divided a couple of coffees, or about 70, that we brewed for this experiment. So every 5 seconds, we would change the cup to which the coffee is flowing. So it's a horrible experiment because you have to have 12 cups, and every 5 seconds, you switch the cup. And then we measured TDS, so we measured the amount of coffee in every sample within an experiment. And this, how do you measure the amount of coffee in coffee? Well, the brute force method is to just dry out the coffee, the liquid, and check what is the mass of the grains. But what you can do is an indirect method where you can measure the index of refraction. And the index of refraction, with this refractometer, the index of refraction is proportional to the TDS, so you can measure TDS by optical measurements. And so what we see is that the TDS changes in time, well, like this. So initially we have very concentrated coffee. So the first drops of coffee, and you can see that actually in the machine, that the first drops are very dense, very dark. As you wait, this intensity decreases. And finally, after the 40th second, you dissolve very little. So there is the mass of coffee in coffee is negligible here. At the same time, the flow rate, well, I showed you one curve presenting the flow rate. The flow rate initially increases and then stabilizes. So if you multiply one by the other, you get the flux of coffee that goes to the cup. And well, I'll show you that in a, oops. This went to sleep. Oh, I think it ran out of batteries.
So
anyway,
go to the analog.
Doesn't matter. And we'll come back to this dissolution. But what happens when we change the pressure? Well, let's look at the pressure. So here you have different pressures. So this is all color coded. So we have different pressures here, ranging from 2 bars to 12 bars. So we have to modify our coffee machine slightly to have this wide range of pressures. But yeah, we could almost brew it at atmospheric pressure and then brew it at very high pressures. And so for different pressures, here is the mass in the cup relative to, it's centered at the moment when there is 10 grams in the cup. So we just shift the time here. So you see that at different pressures, the slope of this curve is different, but perhaps it's best seen in the flow rate. And so the lowest pressure is the yellow bar. So the yellow curve, well, it saturates very quickly and is fairly low. Then you increase the pressure, so you go to these red curves, and that red curves, well, they go quite high, and the flow reaches 2 grams per second, and then it stabilizes. But then if you increase the pressure even more to like 12 bars or 11 bars, then you get this curve. So the final flow rate is actually low, which is surprising because we would expect from Darcy's law that the higher the pressure gradient, the larger the flow. So there's something interesting going on here. And in fact, if you measure this saturation flow rate for different pressures, you find that at low pressures it increases, but then at pressures of about 6 bars it saturates, and maybe even goes down a little if you increase the pressure. And so this was the first moment where we thought that there's something interesting about this, because there's definitely not Darcy-like behavior. There is this linearity is maybe there for low pressures, but definitely not at high pressure. At the same time, there is often, you see advertisements of coffee machines that say, well, this machine is capable of producing 20 bars, 25 bars. So is it true that the higher the pressure, the better the coffee machine? Well, this shows something different, that at some point the pressure stabilizes the flow rate. And so the conjecture is that at low pressures, maybe we see a Darcy-like flow, but definitely at high pressures, we see the saturation. And this is something we wanted to explain. And one idea that we had to explain this is that coffee is in fact a porous medium that is elastic, not only porous, but elastic as well. So what I mean by that is that if you induce a pressure gradient in coffee, in this porous coffee medium, if you induce a pressure gradient, well, then pressure gradient will induce stresses. The stress will cause deformation. So stress will cause strain, and this deformation will change the porosity of the sample. So how many pore spaces are within this ground coffee? Now, this porosity affects permeability. So it affects this material characteristics of how permeable the material is to flow. And so this in turn will affect the flow rate. And so we decided to build a simple theoretical model that would explain or include this compaction. And so the idea is that at pressures that are high enough, the pore spaces are being closed. And so as a result of this, at higher pressures, the permeability goes down. And so that might explain why at higher pressures, the flow rate doesn't increase. So writing the equations of mechanical equilibrium, so this is a well-known concept from the theory of elasticity. So under a stable pressure gradient, this compacted coffee is in equilibrium. And then assuming that stress and strain are related by a linear relationship where Y is the effective Young's modulus of the coffee. And then we need to relate the porosity. Well, we need to relate the strain, so the deformation, with the porosity. And so this is the relationship that relates them. And now the porosity is related to permeability by this Karman-Tasseni relationship, which is another empirical relationship that people use to describe porous media. And then finally, the flow rate is related to permeability and the pressure gradient by a Darcy law, but this Darcy law has now this permeability that depends on the porosity, that depends on the deformation, that depends on the pressure. So here, the flow is proportional to the pressure gradient, but it's also proportional to something that depends on pressure in a non-trivial way. Okay, and so this model can be solved. Exactly. And if we get a model, well, we can compare the model with our experiments. And so this is what the model predicts. So the model predicts that indeed, for low pressures, we have an almost Darcy-like increase, an almost linear increase in the flow rate, but at higher pressures of about 6 bars, the flow stabilizes. So this leads us to the conclusion that perhaps we understand what's going on here, that at high pressures, well, at low pressures, when the pressure gradient is not too high, then this porous medium behaves like a Darcy medium, but at higher pressures, this compaction happens, and so the high pressure is compressing the pores, and by that, it decreases the permeability. Now, this is all in the long time regime, when everything that we could dissolve is already dissolved. in the short-time regime, it's more complicated because at the same time, we have dissolution, and dissolution is something that removes material from the coffee, so it opens the pore spaces, and this compaction, which closes them. So there is a competition that goes on during dissolution, and this competition leads to structural changes in the coffee pot. So these are simulations of what happens in a medium that is that has a non-homogeneous distribution of permeability as the fluid penetrates through it. And what you see here is that upon this erosion, upon this mechanical erosion, channels are being formed in this non-homogeneous sample. And so this simulation shows the formation of channels, or as some people call them, preferential flow paths. So what happens is, if you have a sample that is non-homogeneous, then it might dissolve in such a way that channels are formed. And then these channels, they focus most of the flow. And in coffee, this phenomenon is known as channeling. And this channeling is really bad for the coffee, because you get a flow rate that is good. So you get the flow rate that you would expect for your coffee, but then the dissolution is very low because the fluid, most of the fluid doesn't dissolve the coffee, but instead goes through these channels. And so in the case of coffee, this channeling can be manifested, well, how you can see it. What we did is we took a coffee pot after brewing and we put it in a CT machine. So we did X-ray imaging of this coffee pot, and that's thanks to the fact that in the physics department we now have a CT machine. So this was, I think, first in the world photo of a coffee pot in a CT machine. So dark areas, white areas are where coffee is, and dark areas are where the pore spaces are. So there's a 3D reconstruction here. So this coffee has definitely channeled. This is already after brewing, so this is empty space. So what happened here is water found this channel here, and it spread over the coffee pot. And then finally, well, it seeped through the bottom part of the coffee cake. So this is an example of what is undesirable in coffee. We want to avoid it, and the way to avoid it is to make your sample as homogeneous as possible, because every irregularity, every change in porosity, every distribution of porosity might lead to the formation of channels. And that's why we pay so much attention to homogenizing, mixing, and shaking this coffee bed before we make the coffee, so that this doesn't happen. Another way, well, now that we know that this channeling happened, we wanted to understand how does the coffee, this porous medium, move, or what happens during the brewing process. And it's hard to look into it because it's closed in a metal box during brewing. Metal boxes don't really image well with X-rays. So what we did is we did the before and after, but we added some tiny glass beads of the size of about 50 to 70 microns. So we added these glass beads to coffee, and so this is X-ray microcomputed tomography before brewing. So we note where the positions of these glass beads, and then this is after. So what you see here is that after brewing, there's different contrasts, but essentially after brewing, there is these cracks that appear, and these cracks cause the sample to be less homogeneous. Now, what we want to do, and what we are in the process of doing, we have three-dimensional images of before and after, and we know where the glass beads are. So now the job is to correlate the positions before and after, so that we get a displacement field, and we know which parts moved during brewing and in what way. And so this is one of the works in progress in our lab. But this shows us another thing. So if this is before and this is after, maybe you have this experience of making coffee in a coffee machine where you turn the machine on, you start brewing, then you turn it off, and then you decide, no, maybe you want a bit more water. So then you turn it on again. So if you do this repeatedly, this is what happens. So the yellow signal or the orange signal is the pressure. So the pressure tells you whether the machine is on or off. So what we did, we turned the machine on, we would turn it off for a couple of seconds, and then we would turn it on again. And the green signal is the flow rate. So you see that the typical behavior is that the flow rate is initially small, then picks up. So this is, we're brewing our espresso, then the flow stabilizes. So this is something we understand already. Then we turn it off, and then we decide that we need a bit more water. We turn it on again, and the flow rate is completely different. We turn it off again, and the flow rate is completely different. And the flow rate seems to ever increase, which signifies the fact that if these cracks are formed, they produce inhomogeneities in the sample, and these inhomogeneities are prone to channeling. So the more you do it, the more channels appear, and the sample becomes almost like Swiss cheese in which there are tunnels for the water, and so you get worse and worse coffee. Okay, well, perhaps you are not fans of espresso. Maybe someone likes a mocha pot coffee. How many people like it this way? Okay, there's some fans. Well, there is some. Well, what can you do with mocha pot? So this is the most famous shape of a mocha pot is designed by a company called Bialetti, and Renato Bialetti was the son of the founder. And he was so much in love with his company that when he died, he was buried in an urn. And this is the shape of this urn. So this is a photo from his funeral. So this is dedication. Now, what can you do with a mocha pot? Well, this is a very exciting experiment. I told you that it's super hard to look into what's going on in an espresso machine because it's all made of metal. Now, there is a way to look into it. You can use neutrons. So this is a mocha pot that was put into a neutron source. So it's imaged with a neutron beam. And in order to visualize what's going on, instead of water, there is heavy water inside. So the effect of this experiment is that we can see what's going on inside. I'm going to play it in a moment. The side effect is that the mocha pot becomes radioactive for about half a year. So it's a once in a lifetime experiment. But let's see. So this time the principle is completely different. So what you do, you heat up the water from underneath. So it starts condensing here. And so evaporation leads to an increased vapor pressure in this area. This vapor pressure now is boiling. This vapor pressure is pushing the water through this funnel. And here is where the coffee is. And so finally, it's the pressure of evaporation or the pressure of boiling that drives the fluid out through this porous medium and then to the top chamber where delicious coffee is being produced. And so there's a fairly complicated thermodynamics going on there because on the one hand there is constant generation of vapor, then this vapor is pushing so it's this volume of vapor is expanding, but in the end it's enough to drive all the water through the coffee pot, and so we end up having a couple of cups of coffee. And so this was done in the Paul Scherrer Institute in Switzerland. There is another dark side of coffee that maybe you know that if you leave a coffee stain on the table, it will dry out in a very characteristic manner. So what happens is, and it's called the coffee ring effect, that the rim of this stain is darker than the interior. Now, why is that? Interestingly, the same kind of pattern emerges in tea and wine. So pick your favorite fluid and experiment. Now, why is it that the rim is darker than the interior of such a drying droplet? Well, this can be understood by just thinking about how this droplet evaporates. So the classical picture is the following. This droplet is, the contact line of this droplet is pinned. So the contact line of the droplet on the substance doesn't move. If evaporation is uniform, that means from every surface element of this droplet, the same amount of water is taken away in a unit time. But this means that the thickness of the droplet changes non-uniformly. And in particular, because this point or this line is pinned, there's more material evaporates from this part than from the top part, And so there must be a flow that is created inside, and this flow that's created inside, it circulates. So it's a radial flow that circulates outwards, close to the bottom, and inwards in the top part. And this flow is something that brings with it these coffee grains, the tiny coffee grains, particularly the fines I told you about. And so this flow is not strong enough for these coffee grains to make the full circle. So it's strong enough to transport them to the rim, and that's where they get deposited. And so you get these fantastic shapes. And we have a master's thesis in the making in the lab where we investigate how the thickness of this rim depends on the local curvature of the droplet. That's still something that's not quite clear. Okay, and what this brings me to a slightly wider topic of gastrophysics. So all the fluid mechanics that's related to food, which is something I find very interesting. And the result of the pandemic for me and for my 3 colleagues was that we wrote a review paper on culinary fluid mechanics and other currents in food science. And because it was a pandemic and we had too much time, it grew uncontrollably to over 80 pages and 1,000 references. So we put a lot of time into it, but at the same time, it was very much fun. And so if you're interested in the fluid mechanics of food, check it out. We structured it like a menu. So as if with a nice dinner, you start off with kitchen sink fundamentals. So all the rules of fluid mechanics and all the laws that we might need to understand what's going on. Then we start with a drink or a cocktail, which is an excuse to talk about multiphase flows. And once we've had a couple of cocktails, there comes a soup starter. And soups are typically complex fluids, so not all soups flow like water. They might have more complex internal structure. They might have polymers, which make them respond in a nonlinear way to forcing. So we talk about complex fluids. Then it's time for a hot main course, where we discuss thermal effects, which always have a pronounced and lasting consequences for kitchen flows. And after the main course, it's time for a dessert, and desserts are often viscous, like honey. So we talk about flows at low Reynolds number, and how such flows can be used to understand the fluid mechanics of sweet desserts. Then we talk about granular matter and porous media flows using coffee as an excuse. Of course, if coffee is not your thing, then maybe you're fans of tea, and tea is related to turbulence mixing. And after that, someone has to do the dishes, but maybe it's not that bad, because then we talk about interfacial flows and what happens when surface tension enters the game. And so all of that would not be possible without a wonderful team of people. So in particular on the coffee project, the team of Rados, Pranek, Marysia, and Łukasz. So these are all students in my lab, as well as colleagues from the physics department, Michał and Piotr. And now this paper that summarizes our findings is now in print in Physics of Fluids, so it will be out very soon, but the preprint is already on archive. And again, it would not be possible to fund all that because without our industrial partners, so Coffee Lab, a Warsaw Coffee Roastery, and the Polish company Coffee Machine Sale, who distribute coffee equipment, these things tend to be rather pricey. And National Center of Science is not keen on financing these initiatives yet, but maybe soon, once we have some papers published, we will ask for further support. Now, it might sound funny, but in fact, this coffee business is an excuse to talk about rather complex flow phenomena. And there's a couple of questions that emerged from this study that are really serious scientific questions about the nature of multiphase flows that incorporate both dissolution and structural changes in fluids. And these are more predominant or more popular than only in coffee. And so with that, I'd like to thank you for your attention, and I'm happy to take any questions.
Thanks a lot, Maciej. So I think it's now it's time to actually say that we are opening the new field of studies starting this October, gastrophysics, right? So yeah.
With pleasure.
It was shown. So, any questions, comments, please?
There was one plot that
Yeah.
was in the color blue of sorts when you presented the channels on a paper from 2012. And I wanted to ask if that plot is a theoretical one by computer modeling, and if so, what was the model used?
Yes.
Also, is the resolution that low, or is it just a coincidence that there is something resembling pixels?
Yeah, I think this particular plot is taken from a numerical simulation. And the pixel that you see this was the resolution used, and that's perhaps because it was 15 years ago, and it was rather computationally heavy. And so, as far as I understand, or as far as I remember, this is just a snapshot of a three-dimensional system where they start with an inhomogeneous, in some sense, random distribution of permeability, and then there's the fluid that percolates through dissolves the medium and then leads to, well, takes away the material, and that therefore increases the porosity. And the model used for that, so for the flow, they also use the Darcy flow with an evolving porosity. Now the porosity and permeability are related by a variant of Carbon-Cassini relationship. But for the details, we would have to dive into that paper. I don't remember it that well.
So how much coffee do you produce during one experiment, and how do you utilize it? I mean, how do you dispose of it rather than?
Well, great question. So for example, to make this plot of TDS, so for each of these points, we would have to have, so each of these points represents a 5-second interval of brewing coffee. And to get these error bars, for each we had 7 measurements. So we had to brew, for this plot, we had to brew 7 coffees divided into 5-second bits. Now, so this is just for one pressure. I would love to have that for multiple pressures. I don't have these measurements yet. If I find interested people, we'll do it. But I think we brewed something like about 300 copies to have measurements that went into this paper.
And it happened during one session, or
no, during multiple sessions. So as with many scientific research adventures, we were learning on the way. We were how to make it better and better. And so when we finally learned how to use our coffee machine and how to make the measurements, this took just maybe 3 days to measure everything. But it took us 2 years to figure out how to do it. I mean, it was not our main project, but it received intermittent attention. But yeah, so the amount of coffee that we used was about 300 coffee that we brewed. I think in kilograms, how much coffee we used for all of that project, I think we were in the range of 20 kilograms.
Do you invite the faculty to come by for a free coffee during the experiment? Or?
Of course we did. Of course we did. Now, if we brew this coffee that is longer, right? So if we brew this, if we're interested in this long time flow regime, this coffee that you brew for 60 or 80 seconds is not that tasty. So that's for
the one that you give to the other people, right?
So the long time flow, yeah, I'm not a fan. So we used to have a big bucket where we would just pour in coffee after measurements, and I once tried coffee from that bucket. Not a good experience.
The end of the Darcy curve is the best moment.
Well, that's a very good question. This curve, it so happens, coincidentally, that this is the typical pressure at which most machines operate, 6 to 8 bars. And this, so whether it is the best moment, I would say it's a sufficient moment. So you don't need more pressure to get decent extraction. Also, one of the things that got us into this research was that coffee has this religious aspects to it. So many people love it, many people talk about it. There is internet experts, there is YouTube gurus. People say various things, but they preach that you should do this and you shouldn't do that. You should have this water and not that water. And so at some point, there's claims that are completely unsubstantiated. And I think this poroelastic response, there is a one internet guru who once said that this compaction of coffee is an important effect. He never provided any evidence for that. I think this study is the first evidence that this compaction actually happens. It's the first time that someone has measured it and isolated this physical effect. And so, yes, definitely from that we conclude that 6 to 8 bars is a good brewing pressure, and we don't need 20 bars to brew decent coffee.
So I wanted to ask about grinding.
Yeah.
You showed some scaling, but people say that for particular types of machines, you should grind differently. Why? Why is that? Why can't I, for example, I use mocha, right? And if I grind it very finely, what goes wrong with coffee then?
Now, the grind size also couples to the pressure at which you're brewing. So in a mocha pot, the typical brewing pressures are not as high as in espresso. So if you brew it, if you grind it too finely, you will clog it. This pressure will not be enough for the water to percolate through coffee. And so this is reason one why things don't work if you grind differently. Now we grind more coarsely for lower pressure because also that also affects dissolution, because the brewing pressure translates to how much time the water spends in contact with coffee. So if it's a like French press where the brewing time is typically longer, then you can have a coarser grind so that there is enough time for also for the caffeine to dissolve across. Because the typical sizes of these coffee grains, like half a micron here, is actually the brewing time of espresso is comparable to the time that you need for the caffeine to diffuse over the distance of about this boulder size, so half a micron. So it so happens that the molecule of caffeine has such a diffusion coefficient that over the time of 30 seconds it diffuses about 500 microns.
Okay, so did you explore parameters like time after roasting and how does it change? Because the coffee right after roasting is different than 2 weeks.
I would love to do that. This is definitely, it happens because this coffee gets worse and worse because it loses the CO2. And what happens when it loses CO2, it also changes the dissolution dynamics, because it typically what happens if you grind it the same way, but a different time after roasting, the flow rate is completely different.
Second question is, often tested with Arabica or Robusta mix, or if you try it?
Well, so we used Arabica because Arabica coffee tends to be more flavorful or more delicate. So like the coffee I brought in these laboratory bottles here, this is a mix of Arabica coffees. Robusta is generally higher in caffeine, has a stronger taste, and in some cultures it's valued more, but generally the point is that it's much cheaper. So that's also why it's more popular across the world. And if you like this notion of like strong coffee, then what gives you the feeling of strongness are the very stringent notes of Robusta. So these coffees that are marketed as stronger, or Jacobs, whatever, will make you strong, then these have an addition or additive of Robusta. But if you're for the rubber flavor or whatever, people are able to pay really big money for these specialty coffees now.
If you check the different,
Tell us a question, please.
so the coffee taste depends on the brewing time. Is it because that different chemicals have different solubilities in water, so they dissolve differently?
Yeah, something I was completely silent about, but it's a very important part of brewing coffee, is that all the different chemicals that dissolve at different times, and well, it's a bit of that is in this concept of brewing time, that you start dissolving these bitter notes if you brew for too long. So definitely. Now, well, of course, different coffees, so from different origins and from prepared when you prepare the beans using different methods. So there's dry method, natural method, the washed. So there's different ways in which you can prepare your coffee pre-roasting, and this affects, of course, the taste. So all the chemicals that are there. This is a super complicated topic.
Thank you. about the roasting temperature?
So it's not only a temperature, it's a profile. So these roasters are like preachers again. So they know their machines, they roast by I think generally if you like light roast, which is not the Italian espresso, but rather Scandinavian, it's called third wave now. So these roasters, they roast it to the so-called first crack. So when you're roasting your coffee, it starts cracking at some point, and this is where you stop the process. But then people are experimenting with different profiles, like, well, you increase the temperature first and you decrease it later. And so I think this is like with making wine. The wine is the winemaker's secret, how to make it perfect.
The last will be about some space-related topics. Coffee and microgravity. So there was an experiment led by Samantha Cristofoletti, the Italian astronaut, at the
The first espresso brewed in space.
Yes.
Yes.
So how it works? I mean, is it difficult?
I think that's the very reason why people can have espresso in space, but they can't have, French press. I mean, French press is okay, but filter coffee is harder. That you can easily generate high pressures. Well, I'm not sure how it affects extraction, but I guess that at high pressure, the flow is fairly similar to that on Earth. Now, how do you savor a drop of coffee that you generate in space? Well, I don't know. I would love to try myself. But
Zero G project.
yeah, I think espresso is fairly safe, as in both in space and on Earth, you can work with it.
I don't see any more questions. Do we have anyone on Zoom? You can take a look. Nothing's popping up.
Now we have.
Okay, so let's thank Maciej again.
Thank you. Thank you.
So that was officially the last seminar of the semester, although we have one extra seminar next week. It will be of a guest of Rafael, right? It's a researcher working at Heidelberg and working on some mergers, right? So same time, there will be also information in email. Feel welcome to come
So
here.
let me use this space to advertise that our last seminar of term. So the seminar I co-organized is a Friday morning seminar on soft matter and complex systems. And we will have a guest speaker who will talk about the measurements of angular momentum of black holes. A speaker from Caltech. And I think it's going to be quite exciting. So I will send you the information today, and I will ask you to distribute it to anyone who might be interested.
Sure. Thank you very much. Okay, so we are done. Thank you.